Hi again. While the graphs we have seen so far are nice and easy to understand, when you perform regression analysis, you'll find something different than a scatter plot with a regression line. The graph is a visual representation, and what we really want is the equation of the model and a measure of its significance and explanatory power. This is why the regression summary consists of a few tables instead of a graph. In this lesson, we will learn how to read and understand these tables. Typically, when using stats models, we'll have three main tables: a model summary, a coefficients table, and some additional tests. Certainly, these tables contain a lot of information, but we will focus on the most important parts. I'll start with the coefficients table. We can see the coefficient of the intercept, or the constant as they've named it here. Both terms are used interchangeably. In any case, it is 0.275, which means B0 is 0.275. Looking below, we notice the other coefficient is 0.0017. This is our B1. These are the only two numbers we need to define the regression equation. Therefore, y hat equals 0.275 plus 0.0017 times x1, or GPA equals 0.275 plus 0.0017 times SAT score. So, this is how we obtain the regression equation. Great! Let's take a step back and look at the code where we plotted the regression line. We have plotted the scatter plot of SAT and GPA. That's clear. Next, I've created a variable called y hat. Y hat is equal to 0.0017 times x1, or SAT, plus 0.275. That's the regression line, the predicted variables based on the data. Next, I plot that line using the plot method. Naturally, I picked the coefficients from the coefficients table. Didn't make them up. Okay, how useful is that prediction, you may ask? Well, knowing that a person has scored 1700 on the SAT, we can substitute in the equation and obtain the following: 0.275 plus 0.0017 times 1700, which equals 3.165. So, the expected GPA for this student, according to our model, is 3.165. And that's the predictive power of linear regressions in a nutshell. We are doing great so far. What about the other cells in the table? The standard errors show the accuracy of prediction for each variable. The lower the standard error, the better the estimate. Easy. The next two values are t-statistic and its p-value. If you have followed our program so far, you will know there is a hypothesis involved here. The null hypothesis of this test is beta equals 0. In other words, is the coefficient equal to 0? If a coefficient is 0 for the intercept, B0 that is, then the line crosses the y-axis at the origin. If beta 1 is 0, then 0 times x will always be 0 for any x, so this variable will not be considered for the model. Graphically, that would mean that the regression line is horizontal, always going through the intercept value. Let's paraphrase this test. Essentially, it asks, is this a useful variable? Does it help us explain the variability we have in this case? The answer is contained in the p-value column. As we know, a p-value below 0.05 means that the variable is significant. Therefore, the coefficient is most probably different from 0. Moreover, we are longing to see those three zeros. What does this mean for our example? Well, it simply tells us that SAT score is a significant variable when predicting college GPA. What you may notice is that the intercept p-value is not 0. Let's think about this. Does it matter that much? This test is asking the question, do we have enough statistical evidence that the intercept differs from 0? Graphically, that would mean that the regression line passes through the origin of the graph. Usually, this is not essential, as it is causal relationship of the x's we are interested in. All right. In our next lecture, we will go back to theory for a while to build up your understanding of regressions. Thanks for watching.